Hello guys, my name is Christine and today we will talk about the electrical transmission in axon. So to understand this concept better, we should remember some of the voltage number that is important. First is that the voltage number of sodium is a positive number. The voltage number of potassium is a negative number. And also one idea that we want to remember that if one ion voltage gated channel open, then we will have the membrane potential get closer to the voltage number of that ion. So in this case, for example, if we have a voltage gated channel of sodium, if this gate open, then our membrane potential it will get closer to the E of Na plus, meaning that it want to be positive, right? So it will become positive. And if we have a voltage gated channel of potassium, now it's open. So if this open, then our membrane potential will get closer to the voltage number of K plus, which is a negative number. So this will become negative. So that's the idea that we want to remember, so we can link it to the activity of all the gate channel. When it's open, which one open and which one closed in the electrical transmission through the axon. So now we'll look at the graph of our electrical transmission. We have horizontal line and also we have a horizontal line. So for the horizontal line, it would just be the time. They can be a millisecond. And then in the vertical line, we will have this is the potential. There's some potential that we want to remember. First is that we know that our potential voltage of potassium is a negative number. It's around negative 90 millivoltage. Our resting membrane is negative 70 millivoltage. This is our resting membrane potential. And then there's negative 55 millivoltage, which is this is the threshold. Okay, so the threshold indicating that mean that if our graded potential or any stimulus, if it reach to this point of negative 55, then this will create an action potential. And one characteristic of our action potential is that it is work as the mechanism is none or all or none. So if it reaches the threshold, we will get an action potential. If it does not reach to negative 55 millivoltage, we would not have an action potential. And another number we want to know that we have that our voltage number of sodium is a positive number. So it will be around here. It usually positive 60 millivoltage, and that is for our potassium. Okay. So at first for our membrane voltage, it will start at the resting membrane first, at resting membrane. And if our stimulus reaches the threshold at negative 55, now we will have an action potential, which go up and then go down and then go back to resting membrane. So how do we link all the activity of all the gates in this graph? So what we have is that at first at resting membrane, it will go at negative 70, which is our resting membrane. When it reaches the threshold, now it is going to the positive direction, meaning that it will going to the direction of the voltage gated channel Na plus when it's open. So at this point, we can see that Na plus voltage gated open. So if it is open and then until when it reaches this point, now it started going down. So in order for it to going down, then at this point, we will have our sodium voltage gated channel now closed. And then after it closed, then and the process of going up like this and make the membrane potential become positive like this, at this point we call this a depolarization. And after a while, we will have our voltage membrane will start going down, and we can see that it's going toward the direction of -90, which is a negative number, which is our K plus. So at this point, when it's going down like this, we will have potassium gated voltage channel open. That's why we will have this going down toward the potential number of potassium. And the process of we going down like this is called repolarization. And up until a point when it's going lower than our rest membrane, then at this point we will call this hyperpolarization. And so when it reaches hyperpolarization, we can see that it's no longer is now going up a little bit, so it's no longer going in the negative direction. Hence, at this point, we will have our K plus gated voltage gated channel closed. So up until the point when after hyperpolarization, we already have our Na plus, our sodium voltage gated channel closed, and also we have our potassium voltage gated channel closed. And when it go back up to the resting membrane, and here we'll have this in order to bring it back like this, we will need the action and the activity of the Na plus, K plus, ATPase. Bring into the action to bring this back up. So this is the graph, the general graph of how our membrane potential work and how it is linked to the activity of all the voltage gated channel. As I said earlier, if one ion voltage gated channel open, then the membrane potential work closer to the voltage number of that ion. So that's why we see that we have depolarization is going up to our voltage number of potassium, and then it's going down to our voltage gated channel of potassium. So at first going up to positive direction, a voltage gated channel of sodium, and then it going down to the negative direction of potassium voltage gated channel. So that's why we can see at this point Na open when it go in positive direction. When it's going to the negative direction, then we have the K plus open. And in opposite, if we have it going down in the negative direction, then Na must be closed. And if it's no longer go in the negative direction, then we have K plus closed. And then after that, when all of them close, we will have the Na plus and K plus ATPase to bring it back up to their resting potential. Also, in order for we to receive another stimulus and generate another action potential, we need to have all these gates come back up to its normal cycle, which is at the beginning of resting membrane we have Na plus closed and also K plus closed.